Yeah, it's just it seems it's mostly triangles, and then I think there are one or two people on it sometimes. Yeah, sometimes, yeah.
There's no expectation that anybody asks a question.
It doesn't seem to be. I left the Q and A open, but nobody's ever used it. So. I've turned off their video. Zoom bomb us. like grass here. Grass, yeah. It's like window is open.
Somebody wrote.
The window is not open, but it's broken. Interesting. I must excuse myself if I might get an important phone call.
1, 2, 3. 4, 5, 6.
The reasons.
Board.
That one is, don't give the word. Really? I said stock in you. Huh? I said stock. Yeah, these are, these are. Yes. Yeah, let's go.
Should we start now? I guess I don't know.
Yeah. We are happy to have Leonid Petrov here and going to tell us about something interesting.
Okay, yeah. So they say that to be successful in academia, you have to do something pretty strong and also something that is kind of relatable, that the people who already are doing something understand. So I'm not sure I'm good on the second part here. And most of my talk will be dedicated to explain why, why it's interesting and how it relates to many other things. So it's about random Fibonacci words. And okay, so a Fibonacci word is a word composed of twos and ones, and they're graded by the sum of the digits, and that's why it's called the Fibonacci word, because there are exactly Fibonacci number of Fibonacci words of length n. But and I'm going to define branching on them, and branching structure on Fibonacci words will describe naturally some probabilistic objects that we can explore. But before anything, I can start with two simpler models, which everybody has heard about. Well, not everybody, most of the people have heard about in the audience, and then the connections will motivate what I do with Fibonacci. So the motivation number one is binary words and exchangeable sequences. So these are words of zeros and ones, and they're infinite. And the word really infinite and random, and the word is called exchangeable. The distribution doesn't change if we permute any indices. So I'm going to denote movements by x's, and I ask that for any permutation distribution of this the same as distribution of epsilon up to xn, and how to characterize changeable binary sequences? Well, once you have the exchangeability, kind of the full invariant of this distribution is a sequence of probabilities mn of k, which is the probability that sum of xi from 1 to n equals k. So k takes values from 0 to n, and n takes values from 0 to infinity. So these are what I call coherent measures, and I cannot take arbitrary probability distributions m sub n. They have to be consistent, actually, because once I know what is the distribution at the level n, then I can cross out the last digit, and then mn minus 1 is going to be related to mn, and there are some linear relations of the form. So if I have mn plus 1 of k plus 1, and I cross out the last digit, then it better be a 1 to get this, but also there is a second case where I have k digits, and then crossing out, I must be crossing out the zeros. So these are, this is the usual conditional probability formula. So coherent measures, there are some kind of, solutions to linear recurrence, and I want them to be non-negative to actually describe a probability model. And exchangeable binary sequences are characterized by what's called the Fibonacci theorem, right? Saying that, well, basically, the most natural examples of exchangeable sequences are IID coin flips, and then Fibonacci says that basically any exchangeable sequence is a mixture of IID coin flips. So so you can formulate by saying that extreme exchangeable sequences are exactly Bernoulli IID flips, which are governed by a parameter between 0 and 1. Okay, a mixture means that you take a mixing distribution mu on segment 0, 1, and then you sample the exchangeable sequence in a two-step procedure. First, you pick a p from the distribution mu, and then you do conditional independent coin flip, and that's how you get the exchangeable sequence. And then you can recover the mixing distribution by having the log-line numbers that this thing converges to the distribution mu. So you would expect this will be a expected value of x1, but in the exchangeable setup, this is going to be the non-deterministic limit. So a particular example is the Poya-Ernst scheme, where you have you have a urn with a black and white ball, then at each step you pick a ball and then double it and put the ball back and then add a ball of the same color, and then xi is going to be the the indicator that the ball is black that you pick out at time I, and then the distribution is going to be uniform in the segment 0, 1. Okay, that's one example. Okay, so right, so the branching of the branching structure in this problem is the Pascal triangle, and I can take time to be to grow in this direction, and at each time I can count how many well, I can index the set at time n by k from 0 to n. This would be n equals 0, and coherent measures are coherent systems of measures are probability distributions on levels of the Pascal triangle. And what I want to emphasize here is that the Pascal triangle structure has two very distinguished paths. That's how you can escape to infinity. So, but first of all, I can say that if I look at n as a growing time, and if I draw the graph of the partial sums x1 plus xn, then this will be just a stochastic process evolving on this graph. And now, if I want to see what if I want to see the slow English numbers, then as n goes to infinity, the random path it goes to infinity will actually land somewhere between 0 and 1 at this point of. So if I rescale the floors, then they will approximate the segment from 0 to 1, and then as n goes to infinity, what I will see here is precisely the mixing distribution mu. So but let's look at the Pascal triangle, and I want to emphasize that there are two very distinct ways of escaping to infinity, which don't allow any randomness. And one way is when you always go up, and the other way as you always go down. And of course, if you always go up, you get to delta measure at 1, or you get to delta measure at 0. So I would call these ways the lonely paths in the Pascal triangle, and they're characterized by the fact that when I go along the lonely path, then there is only one way that I could have come to this path, meaning there is only for each point on the lonely path there is only one way I can go down, which is not true here. And so there are two lonely points in the boundary of the Pascal triangle. And actually, the whole boundary, you can think of this as a convex interpolation between delta at 0 and delta at 1. And you can even realize this probabilistically by saying that, well, if I have a there is a flow that you can make. Suppose that you have a IID coin flip sequence with parameter p, and you want to change p. Then you take the IID sequence and then you cross out. So if you want to decrease p, then you cross out some ones and turn them into zeros independently. This will just give you some other point, or you can replace zeros by ones. So there are ways of going around this boundary inside the sequence. Okay, so this is all very nice, but very well explored. So another motivation for the Young Fibonacci is the Young lattice without the Fibonacci. So it's a lattice of Young diagrams that are branching by adding one box. And here you can define all the structures like coherent measures, and the coefficients in front of this recurrence are going to be the ratios of the path counts. So I'm going to define f lambda to be the number of paths from 0 to lambda, and then the coherent relation is going to be plus 1 of lambda, and then here I'm going to be taking f lambda over f mu, the coefficient. Okay, so lambda has n plus 1 boxes, and lambda is actually a mu plus box. And then a remarkable property of the Young lattice is that the coherent systems and the classification theorem solves the problem of irreducible characters of the infinite symmetric group. So it's a very well it's a very interesting and important representation theoretic problem. And the answer so I don't really need the answer for this problem, but it's given by two people independently. One is Thoma from 1960s, and earlier by Edrei in 1950s. So Edrei was classifying totally non-negative topless matrices, and Thoma was classifying characters of the S infinity. And what I want to show is that is the role of Schur polynomials in this business, which is going to be relevant for the Young Fibonacci story. And so the extreme coherent measures here are given by specializations of Schur polynomials. So the theorem says that extremes are given by the following formula. So you take f lambda, and then you multiply by s lambda of something, where s lambda is the Schur polynomial, and what you put there parameterizes the boundary point. So it's a triplet of parameters, alpha, beta, gamma, where alpha and beta are sequences of continuous parameters. Gamma is another continuous parameter, such that the sum of alphas plus betas plus gamma equals 1. And as long as the Schur polynomial, you start with defining Schur polynomial in finitely many variables. It's a determinant. You can have many determinantal formulas for the Schur polynomial, and then you ask how you define it for infinitely many variables. What you can put inside, such that the Schur polynomial still makes sense. So the role of Schur polynomials with respect to the Young lattice is also because their Pieri rule reflects the branching. So along with being extreme, they also satisfy the following identity, which is what's called the Pieri rule. So in the sense, you can say, well, Schur polynomials are harmonic functions on the Young lattice on one hand, but on the other hand, they are also extreme. Okay. So in the Young lattice, there are also lonely paths, but there are also only two lonely paths, right? So how do you make a lonely path here? Well, you need to either go and only grow one row, or grow one column. So there are only two lonely paths. There is no, you don't gain anything with respect to, like, if you pass from the Pascal triangle to the Young lattice, the lonely paths are still going to be pretty limited. So what else did I want to say? Right. So the classification of the boundary in the Pascal case or a Jeanne case is also equivalent to finding positive specializations of these functions. So we have functions that govern the branching, and we ask what variables or what instead of variables we can put inside Schur polynomials such that, you know, as lambda stays non-negative for all possible lambdas. And the answer is precisely going to be, you know, these parameters alpha, beta, gamma, and they describe the extreme extreme coherent systems. Okay, so that was a there were two reminders about existing results, and I hope I mentioned everything that I'm going to extend to the young Fibonacci lattice. So how does, you know, what is the young Fibonacci lattice? How was it invented historically? So historically, the young lattice carries one important combinatorial property, which is that of a differential poset, and the differential poset property allows to prove some facts about the young lattice in a pretty general fashion. So the differential poset property means that if you take a Young diagram, then there is always one more box that you can add to the Young diagram versus subtract from the Young diagram. Okay, so every Young diagram has four, has, you know, if he has k plus 1 edges upwards, then it has always k edges downwards. And the differential poset property allows to define Plancherel measure and allows to prove in a purely combinatorial fashion this identity, which the sum of squares of dimensions is equal to n factorial. Then you normalize this identity and you define the Plancherel measure. And then Plancherel is f lambda square n factorial. This is a remarkable probability distribution, the remarkable measure on Young diagrams. It's extreme. And on one hand. On the other hand, it is the Askey image of the uniform distribution on permutations of size n. On the third hand, it has a remarkable limit shape. When you take Young diagrams, as let n go to infinity, then Young diagrams have this, you know, remarkable Virchow-Kirov limit shape. And it has many other nice properties. It's a distinguished probability distribution. Now, on one hand, it has all these connections, but on the other hand, it purely follows from the differential poset property. Now the question is, why do we need to define the notion of a differential poset if we only know one example, the Young lattice? Well, it turns out there is another example, which is the Young Fibonacci lattice. And for that, we have also differential poset property and Plancherel measure. Another question is, okay, how can we extend the analysis and can we prove something about the Plancherel measure or its friends? And the friends of the Plancherel measure may be defined through some family of nice functions. And that's the motivation. What can we say? How can we bring what we know in the Young lattice to the Young Fibonacci? So how to define the Young Fibonacci? Well, you basically start with trying to construct. So the Young Fibonacci lattice was defined by Richard Stanley, and I think that what he was trying to do is to construct another example of a differential poset. And it turns out that you can construct it in a kind of a maximal way, that you don't connect edges unless you're forced to. So the Young Fibonacci poset starts with the following. So start with the empty, and I start with one edge, and then at each step, so you can think this is n equals 0, this is n equals 1, and then at each step, you reflect the previous two levels together with the edges. And after you reflected them, so here's my reflected piece, then you force the differential poset property for level n to happen. Once you do that, you never connect anything together. So you let everything to branch maximally. So now with the second level, I have, so at level n equals 2, I have two vertices. Then at level n equals 3, so the yellow thing is what I reflected, but then I need to add two more vertices because this must satisfy the differential poset property and this one as well. So at level n equals 3, I have one vertex from n equals 1 and two vertices from n equals 2. So this is the Fibonacci recurrence that you get from here. So let's do two more levels. So here I have this is reflected, and then I have two more, and then I have three more vertices, and then let me try to do the next level and stop there. So here I get this thing, 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 and here I get this thing. Okay, so these are three, and I need five more from here because every time I need to add one extra. Okay, so that's how it goes. And I can encode this branching by saying that when I encode this by Fibonacci words. So this is the Fibonacci word 1, and whenever I reflect, I add a 2 in front, and whenever I add a new, whenever I add, so this is the empty word. Whenever I add a new edge and a new vertex, then I put a 1 in front. So this is 1, 1, and this is a 2, 1.
What does it add up?
Sorry, this is a 2. Yeah, 2 empty. Yeah, 2 empty. Yeah. Now, if I take this 1 and reflect, this is going to be a 2, 1, and this is going to be 1, 1, 1, and this is going to be 1, 2, and this is 1, 1, 2, and this is 1, 1, 1, 2, and this one is a reflection, so it's going to be a 2, 2, and this one is a reflection, is going to be 2, 1, 1, and so on. Okay. Look at this lattice. It's a differential poset. Therefore, it has a Planck-Charel measure. So I'm going to call the same properties as dim W. So for a Fibonacci word, dim W is going to be the number of paths from empty to W. And I can have the Planck-Charel measure. Just by the abstract clear differential posets. Notice, however, that this lattice has a ton of lonely paths. Because every time you add 1 in front, you can keep adding 1. And so it's easy to convince yourself that lonely paths must be extreme. Because, the boundary of a branching graph is composed of all the ways you can escape to infinity in some nice regular manner. And the lonely paths, because they're lonely, because there is no backtracking, they must be extreme. There is no way you can obtain them as a mixture of other things from the boundary. So this implies that this graph has a big ton of lonely paths, and all of them form the boundary. And I can call them call the lonely paths to be, and denote them as 1 infinity W. So 1 infinity W is lonely paths, and they must belong to the boundary of this thing. And also, it turns out that the Planck-Charel measure is also extreme, also belongs to the boundary. And so the boundary of this object is actually composed basically of these two objects and interpolations between them, convex interpolations, much like in the Pascal case. So the boundary, which is obtained by Goodman and Petrov in 98, is the following. So you have this Plancherel point, and you also have lots of, 1 infinity, followed by Fibonacci word of a finite size, of an arbitrary finite size, and then you connect these objects by a segment as a continuous segment, which the coordinate on each segment is basically telling you how much. So you start with the lonely path, but then you mix it with the Plancherel growth by saying that, well, let me pick a random time, and then let me grow as Plancherel for the initial part, and then let me grow as a lonely path for the final part of the measure, or you can exchange them. You do the lonely path first and Plancherel second, and this proportion determines the coordinate on each of the segments. That's all. Like that's the boundary of the Fibonacci. Yes.
Maybe I don't understand what the lonely path is, but can you give an example of one that's not just going up the top or down the bottom?
It's you pick a Fibonacci word, so and then you just keep adding one.
Oh, I see. So not starting at the.
Yeah.
I see.
Yeah. So it's 1 infinity followed by some other word. Yeah. Right. So the description of extreme measures here is not as nice as in the other two cases because, well, you'll see the question.
These are measures somewhere.
So these are once you have the branching structure, you have the so this scheme that I'm applying third time here is that you have a branching graph. It leads to a notion of coherent measures, right? And then coherent measures form a convex set, and I'm looking for extreme points of this convex set. Okay, and so for this model, the set of extreme points looks like this. So you can take any probability measure on this, infinite branching star and define a growth process on the graph. So Goodman and Karov described described the star, and then the asymptotics of the Plancherel measure was done by Leonid and Petrov around 2000. So they proved that the Plancherel random Fibonacci word has lots of twos. So they proved that the random Fibonacci word, if you decompose it as 2 to some number h1, and then followed by a single one, then 2 to some number h2, followed by a single one, and so on, then they proved that h1 over n converges to a beta distribution with parameters 1/2 and 0, which is which has a density of actually 0 1/2 has a density root of 1 minus x. Sorry, 1 over square root of 1 minus x and 0 1, and then independently h2 over n minus 2h1 converges to the same thing, but converges to another beta which is independent from the first one, and so on. Basically they proved that all the random Fibonacci words, they behave like this. So there is no limit shape, but on the other hand, the recursive structure of the Fibonacci process kind of is reflected in the Plancherel measure, and that at every time you find one, you restart the process, and then you pick a beta random variable and you sample an independent sequence. It's a sequence of twos of independent length, and then you continue, and continue up to infinity. So the distribution of the sort is known as a stick breaking scheme because and this particular distribution is known as a gem 1/2 distribution. It's known in population dynamics in probability theory. So the stick breaking continuous process is that you take a stick of length 1, then you randomly pick a point and you break the stick, and the left side of the stick you put aside, but then on the remaining side you repeat the process, just rescaled to this next segment, and then you continue breaking. So then you get the relative lengths of the sequences of 2s. Yes.
So it seems like you wrote your words going to the left,
Yes.
but you wrote the word kind of going to the right.
Well, it's a word that I read like this. So I pick very large n, and then I pick a random word of size n according to the Planck distribution, and then I decompose it like that, and
You take a point in the boundary, then you restrict to level n, and that's the thing.
right. So yes. So this is right. So this is w equals n, and then n goes to infinity. Yeah. So right, I wrote the word from the left, but also I encode it from the left somehow. Okay. So why is it 2h? Because I have to normalize by the size of the next word. So if I throw this away, okay, maybe 2h minus 1.
What is the next one? It would be h over.
Yeah, so it's going to be minus n h2, 2h1, 2h2, minus 2. So you always remove the prefix and then you look at the next word.
2 count as 2.
Right, because you normalize, right? So the size of this Fibonacci word is 6, 10, 12, 14, 17. Yeah. Because if you normalize by some other way, you don't get Fibonacci. Right. Okay. So that's about it. Like what before our work with Jeanne Scott that we posted last December. This was basically the state of the art of what probability can do with Fibonacci's, besides the applications to symmetric groups that were done by Gnidin before. And what we set out to do is like, okay, so can you understand something probabilistic, something asymptotic about other coherent measures, extreme or not? And what we found is that, first of all, there are symmetric functions associated with this graph that are not extreme. So there are some versions of symmetric functions here that are that were introduced by Okada, 94. So very soon after the graph was introduced, Okada said, well, if it's a branching graph, then it must describe branching of some representations or characters of something. And so invented the algebras and invented characters, which are known as clone-Schur functions. They are not symmetric, or they are not. They're not symmetric, and they're polynomials, and they're defined in a recursive manner using tridiagonal determinants. So I can start with 2 sequences x and y, and I can define tridiagonal determinants. So I can define a sub k to be a tridiagonal determinant of the form x1, y1, 1x2, y2, 1x3, y3, and so on. So it's a k by k determinant. And then I need another one. So this one is a standard tridiagonal Jacobi matrix. And the other one is not a standard. It has doesn't depend on one of the. Hold on. So it doesn't depend on y3. It doesn't depend on x2. So AK is a determinant like this, and BK is a determinant of y1, x1, y2, 1, x3, y3. And then here you start repeating x4, y4, and then 1, x5, y5, and so on. So this is going to be plus 1 by t plus 1. So this product somehow takes care of the reflection property in the Young Fibonacci lattice. So and then you define the closure functions by looking if the word starts with all ones. So if the word is containing all ones, then this is just going to be the determinant AK. But if the word starts with a bunch of ones and then a 2, and then some other Fibonacci word, then you are allowed to peel off, this part, and then it's going to be SU, and then you shift the parameters, shift X and Y by K, by shift X and Y by, oh, you don't shift X and Y, you shift X and Y in the B determinant. So take the B determinant and you evaluate it at shifted sequences by absolute U, and then you multiply by the original functions. So anyway, so you define some formula, some products of tridiagonal determinants that are playing the role of the Schur polynomials, and they play the role of the Schur polynomials is that they satisfy the area rule. So suppose you take xn plus 1 multiplied by SW, then it's going to be the sum of SU, where U is above W. So basically, there are functions who branch whose branching reflects the graph structure, and they're not symmetric, right? And the ordering in the X and Y variables is very important. But there are kind of harmonic functions naturally associated to this graph. Now here's a complete divergent from the theory of Young lattice, because Schur polynomials both serve as the branching of the Young lattice, and they also appear as extreme characters. Now these guys are not extreme, but they serve the branch. So finally, I can formulate like what we did, and what our results are over here in terms of Schur functions. So what we did is kind of fix this problem, and we do the following things. So first of all, we classify sequences XY such that these guys are non-negative for all W, because even if they're branching like the graph, then they're not necessarily positive. So we solve the positivity problem, and the positivity problem is not equivalent to the boundary. And the second question is, so we call these Fibonacci positive sequences. And the second question is, if you have a Fibonacci positive sequence, how do you understand what is this distribution on Fibonacci words or on the boundary, right? So for Fibonacci positive XY, what's happening on the boundary? Then we find examples where we have some deformation of the stick breaking construction, or we find some other completely different behavior, which is, either the random Fibonacci word grows like I showed in the Plancherel case, or maybe it stabilizes and becomes a measure on lonely paths only. So how do you approach this problem? First of all, what does it mean to be non-negative? Well, it means that these matrices these matrices A and B must be non-negative. In particular, matrix A must be non-negative. Must have all determinants, all principal determinants be non-negative. Well, it turns out that for a tridiagonal matrix, having principal minors non-negative is equivalent to for a matrix to be totally non-negative, meaning principal minors imply all minors are non-negative. If all minors are non-negative, then this places the problem in the realm of total positivity, and total positivity for topless matrices is equivalent to the Young lattice boundary problem. But for the tridiagonal matrices, the total positivity problem is actually equivalent to a Stieltjes moment problem. So you take a Jacobi matrix, and what you find is you can define, well, if you define, right, so I take the matrix A, which is x1, y1, x2, y2, and so on. And from it, I can view it as a Jacobi matrix, so I can define orthogonal polynomials, monic orthogonal polynomials, by saying, let me take a little. Here, so Pn plus 1 of u is going to be u minus xn plus 1 Pn minus. Right, so I define orthogonal polynomials using this as a tridiagonal recurrence matrix, and by the results of basically going back to flageolet and then repackaged and improved by Sokal and co-authors, matrix A being totally non-negative is equivalent to the fact that these orthogonal polynomials are going to be orthogonal with a non-negative Borel measure on 0 infinity. So A totally positive is equivalent to the existence of a measure nu on positive half line such that PM nu is equal to 0 and not equal to m. So it means that right. So and then moreover there are other connections. You can form moment generating function of the measure nu, and the moment generating function is going to be equal to a continued fraction that you can construct using xi, yi. Now, Jacobi continued fraction that you can construct from x and y, right? But this is only the part of the answer. So the Fibonacci positive sequences must be subset of these guys. So in this way, you get some notion which is vaguely understood so far, is that what are the Fibonacci positive measures? That they satisfy stronger total positivity, because along with A, I also want my B matrix to be non-negative, to be totally positive as well. And so what we find is that we still can classify them, but so far we cannot find the general criterion at the level of these measures. What does it mean to have total positivity, to have Fibonacci positivity for a Borel measure? But on the other hand, at the level of parameters x and y, we have a complete classification and parametrization. And here's how it looks like. So we prove the following theorem, is that xy to be Fibonacci positive is equivalent to the representation that sk equals ck1 plus tk minus 1, yk equals ck equals 1 tk. And make sure I'm not mixing any indices. Right, and then ck is arbitrary positive sequence, and t is basically a sequence that determines the whole behavior, because you can ignore ck's, and if you change ck, then the corresponding coherent measure on the Young Fibonacci lattice doesn't change. So the sequence T must satisfy much more, must satisfy very strong properties. There are two cases, and first case is Right, I can form infinite series, this format, and the first case is that this thing diverges, and tk grow be fast, and the second case is if the same series converges and plus some other inequalities that I'm not going to write down. So we form this infinite series. Either it converges or diverges. Depending on that, you have two different types of conditions. And what we prove is that this is a complete answer. The idea is that, well, you might think then, right? So then what else do we find? So another thing we find is that because there is this strong connection to orthogonal polynomials, then we can go and look at existing orthogonal polynomials and check if orthogonal polynomials are Fibonacci positive. Some of them are, most of them aren't. So we have Charlier and some other types, Q-Charlier, some other Al-Salam, Harlitz, and Al-Salam Chihara number one. I mean, there are like just isolated 6 or 7 families of orthogonal polynomials that satisfy Fibonacci positivity. In the Q cases, the orthogonality of these polynomials has to be taken for Q bigger than 1, which is very different from the Q less, well, which is opposite to the Q less than 1 that's typically assumed in the literature. So there is like, you know, the same family of polynomials is orthogonal with respect to one measure and another measure. That's not unheard of. And what we find is in all these cases is that the orthogonality measure nu in the moment problem is going to be discrete. So in the Charlier case, it's the Poisson distribution. Just the usual vanilla Poisson distribution. In these cases, there are some much more exotic measures with Q weights and atoms located who knows where, but they are still discrete. So we couldn't find continuous measures yet. Maybe the conjecture is that all Fibonacci measures, all Fibonacci positive measures should be discrete. I don't know. And then based on this dichotomy, somehow orthogonal polynomials fall into both categories. And it's not clear what happens. And then going back to the Young Fibonacci lattice and the boundaries in the last 5 minutes, I can explain the asymptotic behavior of random Fibonacci words. So in the Young Fibonacci lattice, remember the Plancherel measure. The Plancherel measure is extreme and also, of course, well, not of course, but also it happens to be realized as a clone Schur measure. So the Plancherel it just has xk yk equals k. And the fun fact is that once you take this, then all the tridiagonal determinants become very explicit, and you get what you want. And so tk equals k. Yeah. So tk equals k. So if tk equals k, you see that the first condition is satisfied. Okay, so it's a divergent type of a distribution. And by Canadian and Kerr, we know that this random Fibonacci work has growing runs of 2s. And then you might think, okay, well, maybe if I deform this Plancherel measure, then if I get the stick breaking behavior and the scaling limit behavior, then I should be here. But it turns out there are 2 deformations that I can tell you. There is a 2-parameter deformation that encompasses. So the claim is that this is positive. This is a Fibonacci positive specialization. If sigma equals 1, it's in the first case. And then for sigma bigger than 1, it's going to be in the second case. Going to be in the second case, and rho is going to be between 0 and 1. And however, what we prove is a scaling limit is that when sigma equals to 1, so we show two Needham-Karov-like scaling limits and theorems, the following sort. So theorem number 1 is that as sigma is equal to 1, then your Fibonacci word actually grows like this, which means that it has scaling sequences of all ones, and you get the stick breaking in the same way. But you get Jeanne with a different parameter. So it's not only 1/2. It actually is 1 minus rho, I think. Double check. Rho, yeah. So you get Jeanne the parameter rho, which means that it's a stick breaking construction where you are breaking the stick, but with a beta distribution with the parameter rho instead of 1/2. Okay. And the second theorem, what we get is when sigma is bigger than 1 and rho is exactly equal to 1, is that our right. So this now that infinite series converges. So it's a very different specialization of how even though you have a continuous parameter family. Now our word grows like this, but there is a catch. So you have a dependency breaking behavior of the following sort. So imagine you're breaking the stick, and H1 is going to scale proportionate to n, and then H2 is going to scale proportionate to n, but you would only have finitely many H's that scale proportionate to n. And somehow, at each time you break the stick, you actually flip a coin. And the flip of a coin has probability of success that goes to 0 geometrically. So you have, you flip a coin each time, you have less and less chance of having a success. And once you have a failure, you stop, and your random Fibonacci word has a growing tail of 1s after that. But not only that, it actually gets better, because it's not like this behavior doesn't actually catch all the 2s. So it turns out that eventually there are more 2s in the tail that this limit theorem doesn't catch. And actually we actually prove the third theorem is that in this regime the number of 2s over n goes to 1 over 1 plus sigma. So if sigma is equal, actually 2 over 1 plus sigma, sorry. So it's 2 over 1 plus sigma. So if sigma is equal to 1, this is exactly, the whole word is basically consisting of almost exclusively 2s. But then if sigma is bigger than 1, then this behavior is, you have a few initial pieces of 2s that scale proportionate to n, then you have a growing piece of 1s, which I don't know how to say anything about so far. And then you have more 2s, and the total number of 2s is bigger than what you get from here. Okay, so the bottom line is that it's a weird and marginal world of Fibonacci words, and however, with the experience from integrable probability, Young lattice, and techniques, we can say a lot about what happens there and get some interesting constructions. Many things are parallel between Young lattice and Young Fibonacci, including that the Plancherel measure actually corresponds to some other map applied to uniform distribution on permutations. The Fibonacci solitaire is a replacement for the Askey algorithm. There is another replacement. There are a few replacements for Askey algorithm. And so basically, having a measure on Fibonacci words, we can define distributions on permutations that are of interest. being, uniform distribution is the most interesting, but there are other deformations. And somehow, somehow this world is, even though it's pretty alien, I would still say it's interesting. Okay, thank you.
Questions for me?
Yeah, I want to ask, what is special about the Fibonacci sequence? Can you just take any sequence, say an plus 1 is an plus 2 times an minus 1, then you reflect twice?
You reflect twice. But you don't have a differential poset property.
So that's,
Well, you have to start with something.
you just take any sequence. Why? What is special about Fibonacci? You
Right.
use here.
Somehow the differential poset property is special. To me, I mean, that's how it started, like historically. Why this thing is there is because it has this differential poset property. Plus Okada algebras. There is an abstract nonsense saying that every branching graph would actually correspond to some algebras and characters of them or whatever. So for every branching scheme, including what you propose, should have some kind of algebra and representation theory associated to it. Now, question is there anything nice you can say about it? You have to start with something. So the differential poset property is one thing you can start with. Well, if you always reflect twice, you get a two differential poset property. That's a known thing actually. It's not unheard of. So you might get a lot there. You might get some mileage from there. Yeah. There are other versions. There are, the clone Schur functions allow you to define truncations of the Young Fibonacci lattice. And the first truncation is the Pascal triangle. But there is one more. The next truncation is the Pascal Christmas tree. Basically, that looks like this. You have, 3 halves of the Pascal triangle that are glued together in the bone. And then what we think is that, every truncation of the Pascal triangle, of the Young Fibonacci looks like, more and more branches of the Pascal Christmas tree. So the next one will be 5, of course, not 4, because Fibonacci. And, now the question is, can you describe the boundary of this thing? Well, conjecturally, it's a, in this case, it's a, like a Y symbol, right? Topologically, but it's not evident that this is the case. Right, so there are more branching graphs you can think about. Yeah.
Yeah.
Is sigma bigger than 2 or bigger than 1?
Sigma bigger than 1, yeah. So sigma equals 1 is.
And when you wrote sigma bigger than 2.
Thank you, yeah, that should be 1. Thank you. Yeah, so rho equals 1 and sigma equals 1 is back here. But then general rho and sigma equals 1 is the orthogonality measure for the polynomials is the Poisson with parameter rho, for example. So it's very classical, branching the Jacobi coefficients for the Schur polynomials with the parameter rho. But there are other things, of course. So we like how this stuff got connected to orthogonal polynomials and Jacobi matrices and total positivity, Stieltjes moment sequences. There are Motzkin paths. There are, moments of the distribution nu all have combinatorial interpretation thanks to all these connections. So there's like more I could say, but I thought I better, instead of just jumping into Young Fibonacci, I thought I motivate why at all you would even think about it.